Okay, let's start. We have two lectures today, so for people who are interested to learn more and not watch the video at 5, we have the second installment of the feedback saga. So I would actually, if you can make it at all, I think it would be probably better because we're gonna. I don't know how much I'm gonna get to it through it in this lecture, but some of the more general, harder concepts of return ratio and kind of feedback analysis with loading will actually happen at 5. Not intentionally, but just that's how things fell out. So maybe it's more helpful to be there live, but you can always watch webcast. We'll see how far we get today. Okay, so what we did last time was kind of looked at the types of feedback. So we went through feedback, and depending on kind of the input summation topology, as well as the sensing network at the output, and depending whether it was current or voltage, you had shunt or series type connections, and that then defines 4 types of feedback. So we're gonna go. We started going through each one of them. So last time we did series shunt. So we're gonna go through the other 3 just so you have it all in one place. This time, sort of with idealized feedback circuits, meaning they're not loading really the amplifier. And then we're going to go, next lecture, look at what happens with loading. So the next topology we're looking at is shunt-shunt. So that's number 2. And in that one, we're going to have the source that feeds in. And then the control source is A times I error. A is now transresistance because it turns control current into, or error current into the voltage. Hopefully my display doesn't die today. And so we're going to have VO here. And this would be our essentially basic amplifier. This is I'll just push it like this. Okay, let's do it a little bit differently. Okay, and then we're going to have here the feedback circuitry. So we're going to push I feedback, and that's going to come from the generator. That's a voltage-controlled current source. F times V out, and V out comes from being sampled. So this piece over here is our feedback network. Okay, so now we can kind of, the same way we did before, write out the equation for this. So A equals V out over IE, simply because there's no current flowing through Z naught. because there's an open circuit at VO as well as here. So A is then trans resistance. F will be I feedback over VO. And then here F is transconductance. That means that T, which is AF, is unitless. And this is always the case. So the loop gain will essentially always be sort of a unitless quantity, because you feed, whatever you feed, same quantity will sort of come back at that point. So we have that VO is A times IE. Then from the input network, the IE, which is the error current, is II minus I feedback, which is II minus FVO, which is II minus A times I error. So from what? Yes, that's right. Let me just see. So FVO, we're going to have AF times IR. Okay. So then we have a standard that I error is II over 1 plus AF. Right, where AF, we're going to say it's also T. And then since we have that VO is A times IE, from here we have that VO over A is II over 1 plus AF. Or in other words, VO over II, which is our closed loop gain. In this case, it's a resistor, trans resistance, is A over 1 plus AF. Now, if you take a look at this, it's interesting to also do the quantities like what is the input as well as the output impedance with feedback, right? So we go from lowercase ZI and ZO to capital ZI, ZO. So ZI will be VI over II, and in this case, VI is here. So VI is IE times small z naught over II. And we already have that ratio over here. So that's sorry, this is ZI. So shunt always reduces the input impedance, okay? So by 1 plus T, so shunt feedback. And then what we have for the Z out is that Z naught will be V test over I test. And given that we've already kind of done that in the previous one, we've done series shunt, this one will also be reduced. Right. think for those who forgot, in this case where we had, in the previous lecture, we did a shunt at the output. Right, so it's the same situation, and then from that we got that the shunt also reduces the output impedance. Okay, so the next type of feedback is shunt series. So now the input is the same as we just did, which is the current source into ZI. But the output, because the sensing circuit is in series, we're outputting a current, right? So we have a northern equivalent of the amplifier. And then this is the output current that goes, so again, this is our base amplifier. And then from here, we tie the network. At the output, we're sensing in series. So I0 flows this way. And then we're shunting over here. My drawing is not the best. Okay. And then this is the feedback network. Again, this is the I feedback. So the situation at the input is the same, but at the output we have that I/O is now A times IE, because we've shorted the output, so no current flows through Z0. So all of this current AI goes into I/O. And then again, I error is II minus I feedback, which is II minus FIO. And again, II is AF I error. And so we get that I error is II over 1 plus AF, or II over 1 plus T. And so in this case, the closed loop gain is I/O over II, because we have output current over the input current. So it's A times IE over II, and in this case, A over 1 plus T. If we look at ZI, ZI is the same as in the previous case. So shunt ZI will be small zi over 1 plus T. And then at the output, we have to apply sort of the V-test. So if you apply V-test at the output to figure out what's the capital Z0, you will open the input. And so what you get is that I test is V test over small Z0 plus A times I error. And then you have that F times I test, because now instead of I naught, there will be I test flowing here. So I test will also replicate here and into the feedback. And then because when we do the output impedance testing, we kill the source, then I feedback is equal to negative I error. So this is I feedback is FIT is minus I error. So from there, you have that IT is VT over small z naught plus A times, and then I error is going to be minus FIT. All right, so from here, you have IT over 1 plus AF equals VT over Z naught. Or in other words, VT over IT is Z naught over 1 plus AF. So Z naught is Z naught over 1 plus AF. This is T. So series, again, since this is the series connection at the output, increases the output impedance by 1 plus T. Maybe it's worthwhile just, I don't know if I'm going to have the space. OK, I'll jot it down here on the previous one. Sort of worth down noting just what the equivalent closed-loop amplifier model is. So here you have input current I, and then your impedance is Zi over 1 plus T, which means that it makes sense. If you have a closed-loop amplifier that accepts input current, you want its input impedance to be as low as possible so you can get all the input current from, let's say, a source that is a Norton source. And then the output, you have A over 1 plus T, which is your feedback. And then you have Z naught over 1 plus T, which is your output impedance. So this is kind of the closed loop equivalent. So in this one, which is the shunt series, again we can draw that as well. So I'll squeeze it in here. Again, we have II coming in, and then Zi, which is reduced by 1 plus T. And then here on the other side, we have the current output. So A over 1 plus T II. And then we have the Norton, which is now Z naught. Because it's now a current source, the output impedance is boosted by 1 plus T. Okay. Series. So here we have the Zi, and then the error voltage is now developed on Zi. There is a feedback source, FVO. So that's the feedback voltage. This is the input voltage. And then in the forward direction, the amplifier has turns voltage into, into current, but it's now proportional to the voltage error. We have Z naught, and then the series connection to sense the I naught at the output. Now again, this is the feedback. And this is the amplifier. So again, from here, the input is V error plus F times VO, which is the feedback. For I/O, we can write that it's directly A times VE, because there's no current through Z naught. And then solving for this, VI is VE plus times F. Times I here, since we're feeding back the current. And then this is basically VE. So VE is VI over 1 plus AF. So V error, on the other hand, is the II over, and then we have IO over A, which is VE. Is this. Now, from here, we have that this VE is IO over A. So we have that IO over VI is A over 1 plus AF, or A over 1 plus T. So this is a transconductance amplifier. Right? Now, what we want to look at is that ZI is VI over II. And since VI is the sum of the two, so VI is 1 plus AF times VE over II. And then we have that from here, VE is IIZI. We have 1 plus AF times ZI. So again, the series input resistance or the series connection with feedback increases the input resistance or impedance by 1 plus T. And then we can write kind of the small model. In terms of the output, we already know that Z out is going to be Steve from the previous example. And then the small model for the closed loop will be ZI 1 plus T, and then here the current source A over 1 plus T times VI. and then we'll have the Norton output. And this one is going to be 0 times 1 plus t. So this whole thing will be essentially turning VI into IO, which is transimpedance. Okay. This may all sound a little bit abstract, but we're going to start mapping this to some examples now, so you'll be able to kind of start recognizing, hopefully. So let's take a look at the circuit like this. Should be a familiar one. Okay, so the first question is, what type of feedback is this? Shunt where? Sorry, this is R2. R2, R1. But so when we define type, we define it by the type of the input network versus type of the output network, right? So there's the kind of the summing network, and then there's the network that takes stuff into feedback, right? This is amp, this is feedback, right? So this can be series or shunt, and this can be also series or shunt. Okay. So if you look at this amplifier here with this feedback, which topology this is? Okay, so majority says series shunt. Okay, so let's take a look at how we can massage it so it fits a little bit into kind of what we've shown earlier. Okay, so I can write it. So this box is the feedback path, and as you see, the feedback voltage is in series with the error voltage and forms the V input, right? So this is clearly a series connection, right? And then at the output, we're shunting the output. If feedback was killed here, right, then I would be also killing kind of the variable I'm sensing, which is the V out. So since I'm measuring V out and feeding it back, this here is a shunt connection, right? Okay, so if I assume that Ri is infinity and R out is 0 for this amplifier, then we can go and write out and say that, OK, well, my feedback ratio F is going to be R1 over R1 plus R2, because it's the voltage divider of F. So in other words, F feedback is R1 over R1 plus R2 times VO. So I can say that this is F. Then the standard stuff for the series shunt, the V error is VI minus V feedback. And then V out will be A times V error. And that's A times VI minus V feedback. And this is FVO. So we get that V over VI is going to be A over 1 plus AF, where F is R1 over R1 plus R2. Now, for A large, A closed loop will be then approximately 1 over F, and that's kind of what we know for ideal this type of non-inverting amplifier. 1 over F will be 1 plus R2 over R1, right? Note that isolating this was assuming that the input impedances are ideal, in a sense that since we're sensing voltage, we're producing voltage at the output of the amplifier, the output impedance is 0. And since we're, again, summing voltages at the input impedance is infinity of the amplifier. So it's not loading the feedback network or the source. Now, when you go into more practical configurations, what you will have is something else and more complicated. You will have to, so with, let's say, Ri, finite, and Ro non-zero. Right? Then we have something like Ri, and then we have R1, R2, and we have A times V error, R out, and then we feedback. And then this is VO. So now if you try to calculate ACL, you really only have to do a tedious KVL, KCL analysis. And after a little bit of work, you'll be able to finally do it. But the problem is these components, oops, I don't know why it's turning on the, these components, Ri and R naught, are going to make the analysis significantly different, more difficult, because now you have kind of the interaction, or you have a problem of defining F. If you take a look at how you feed back, this is your V feedback. Now V feedback is not only R1 over R1 plus R2, but you have some current going through Ri, because Ri is not infinite, right? So the amplifier loading the feedback network is going to change what F is going to be, right? So it's not as straightforward to analyze what's happening. Because of that, people have developed kind of a bunch of different methods in which to kind of break the loop and do the analysis. We're going to do sort of one major method, and then just comment kind of on some of the discrepancies that people are doing between the different methods. So if we analyze, so this is feedback analysis, okay, with loading, which is sort of practical. The first method, and which is what we're going to do a little bit, start today, this lecture, and in the next lecture really work it out, is the return ratio method. And in particular, we're going to focus on generalized version. And not sort of the asymptotic version, because there's some, this one is exact, actually. And then the second method is the two-port equivalent. That one is kind of described in detail in the book. So I'm not going to go into it in too much detail because it's A, tedious, and B, you can actually easily make an error if you don't kind of include the loading effects correctly. So we're going to just highlight some of the differences between the two, but mostly focus on the return ratio method. And then in some cases, you could apply Miller theorem to solve the issues, and there are some other kind of approximate methods. But Miller's theorem, as we know, only works when gain is high. So when we do frequency analysis beyond the poles, it will sort of lose the applicability. Okay. We kind of draw out the generalized feedback model. And we'll start from there. So in this model, rather than having, so far we had a notion that the input signal comes in, there is a summing node, there is an amplifier A, we take the output into the feedback into the summing node, and that's it. Okay. When we have the loading effects, isolating what F is versus what A is no longer possible, because as we saw because of RI and RO, these two networks kind of interfere, right? So rather than having this model, we're going to have a little bit more general model that will capture these loading effects nicely. Let's call this a summing node. So this is Sin, this is going to be Si, Sj. Okay, so by having this model, we're accounting for, okay, so hopefully, we're accounting for several things. One is that these two kind of gain elements are giving different ratios at which the signal and the feedback kind of sections interact. And then this is the feed-forward section, which models sort of how the signal that is applied to the input it actually propagates to the output, but not through A, but maybe through F. Okay? Because so far, anytime we drew the F feedback, there was really no, if Rin is infinite, there was really no way for the signal to go through the feedback network out. Right? And in this case, so D is actually modeling that feed-forward behavior. So if we write out kind of what S out is, that will be D times S in, which is this feed-forward component, plus B2 times Sj, which is just this Sj coming to the output. And then Si will be equal to B1 times S in, and then minus H times Sj, which is really the feedback. I'm using a little different terms here on purpose, and we're going to relate them then after we derive everything to sort of the loop gain and these familiar terms that we did so far. Okay. What we have here as well is that Sj and Si are related through the amplifier gain. So as you can imagine, this K really should be your native amplifier, right? So this is amp, and this is feedback. Right? But there are all these other blocks that sort of model how these two interact together when they're put in the feedback configuration. So from here, we can derive that Si is B1 over 1 plus Kh times S in, because we can just take this and replace it in here. And then we can write that S out is D times S in plus B2 times K times Si. Again, we're taking Si from here, putting it into here, and then Sj into this equation here. And so this is D times S in plus B1 K B2 over 1 plus KH S in. So now we have our closed loop gain, which is S out over S in. S is just signal. It's not Laplace or anything. It's just any signal representation that we want, current, voltage, whatever. So in this case, it's B1 K B2 over 1 plus KH plus D. So normally, you could say, well, this piece over here reminds me of A over 1 plus T, right? Where A is the forward or the gain of the amplifier itself, and then T is the loop gain. This piece over here is feed forward, or we can call it feed through. Right? This is only here because of the feedback is is bidirectional. You're going to have that piece going through. Right? If the feedback section is only unilateral, like the amplifier is, you would not have this piece. Right? So ideally, when we did all these shunt series, shunt, our feedback section was unilateral. So we did not have this D component in here. But in general, when you have just a resistor coming back, that component is actually bilateral. So the signal can go either way through it, and you have to take this feed-forward component into account. Now, we can rewrite this a little bit in order to set the stage for the next derivation. You can do B1K, B2. Plus, and then take D times 1 plus KH over 1 plus KH. And then we'll be able to separate out K and then have B1, B2 plus DH over 1 plus KH. And then plus D over 1 plus KH. Doing it this way is sometimes convenient because we can then sort of forget this term because it is the feed forward, but it's attenuated by the loop gain. And as long as we can effectively calculate what this contribution is here. And now you'll see sort of how we can, by nulling certain signals in the network, how we can produce these quantities over here. That's kind of the main goal here, of the approximation. So again, let's just rewrite the ACL. B2. One plus KH. Now, if you look at this, what is B1? Maybe I should rewrite the equations as well, just so you have them. Okay. Okay. So B1 is Si over Sin, given that Sj equals 0. Right? So in other words, if we go back to the circuit, if I null Sj, there's no feedback coming back. So my Si becomes B1 times Sin. Okay? So this is equivalent to controlled source in an amplifier equals 0. Controlled source means that A times V error, right? So that native A of the amplifier is 0. If we had a transistor, that would be GM equals 0, right? Because that's kind of the coefficient that goes multiplies VGS or V pi. And then we have B2, which is S out over Sj for S in equals 0. And that means input equals 0. Why is S in equals 0? Because that feedback path through D is now nulled, right? So my output is just B2 times Sj. Again, it's kind of B2 times Sj is S out if I don't have this path over here. D is going to be S out over S in. Again, if K equals 0. So this also means no controlled source. Right. So if I don't have the controlled source, meaning I disable the amplifier itself, I'm just calculating with D what is the feed forward from the input to the output through the feedback network. Right. Okay. So if we look at this ACL, KH, that's our T, or in this case, we're going to call this return ratio. And we're going to calculate it in a procedure that I'll show you shortly. But right now, let's focus on how do we calculate these two pieces. So D, I've already told you, it's S out over S in when I disable the amplifier, right? So we'll see on different topologies. But the only thing you need to remember is that when you're calculating D, which is the S out over S in, when amplifier is kind of disabled. Okay. But for this quantity, so we're going to call this A equivalent. And then we're going to call this A0. A equivalent is the feed-forward gain of the amplifier itself. However, that amplifier is loaded by the feedback. So feedback does not exist, but amplifier is loaded by feedback. So this is with feedback loading. Okay, so you may say, okay, that's all fine and dandy, but it's a little bit abstract, right? But actually, if you take a look at these values, if I know how to calculate B1, B2, D, and DH, then I actually have a way of calculating this whole quantity from real circuits. So we've already seen here how we can calculate B1, B2, right, and D. So let's take a look at what this really represents. So I can rewrite this A equivalent, which is K times B1, B2 plus DH, with the following: DH over B2 plus B1 times K times B2. And the reason why I do it like this is hopefully going to be apparent shortly. This first component is Si over Sin when S out equals 0. Okay. If you don't believe me, let's take a look at these expressions over here. If S out equals 0, then Sj becomes minus D, so Sj becomes minus D S in over B2. And then Si is B1 S in plus DH over B2 S in, right? So Si over S in for S out equals 0 is B1 plus DH over B2. Okay? So as long as I can calculate how S in maps into Si, when S out equals 0, I find this gain component. Right. So then I have my K, which is, or maybe I should